Okay, so the way we will prove this theorem and other theorems, this is just an example, is using Fourier analysis, which of course we'll talk about after the break, but I'm not going to start it in 2 minutes. But essentially what's going to happen is that we are going to express any function in 0, 1 to the n to 0, 1, any function on the Boolean cube, using the linear function, using the parity functions, or if you want, the characters of the Boolean cube as a group. And once we do that, epsilon bias sets will allow us to actually fool any function depending on how this function is expressed with respect to that basis of linear functions. We will see. Now, Fourier analysis is important in complexity in general, and in pseudo-randomness, to a large extent. If you remember, I told you at some point that maybe that's the third most important tool. Like you have polynomials, you have expanders, like spectral graph theory in general. So you have like abstract algebra, and therefore polynomials, finite fields. You have spectral graph theory, so you have expanders at the core of this, but not only that. And then you have Fourier analysis, which is another like main tool that you use in pseudo-randomness. And I'll give you like after the break, like a 10-minute 101, course on Fourier analysis. It's actually, I will need a few facts, so it's going to be easy. And using those easy facts, we are going to show this theorem and more. But let's take a break and resume at 10 past the hour. Okay, so let's continue. Well, Fourier analysis is a complete course. It's not like a 10-minute part of a course in pseudo-randomness, but it's kind of remarkable what you can do in 10 minutes about Fourier analysis. So what's going on here? So say you have this function f. Forget about PRGs for the next couple of minutes. Right. So say you have this Boolean function the way we started, and now, despite what you might expect, it's actually harder to work with Boolean functions than with like more general functions. So for example, when you add Boolean functions, you get like 0, 1, and 2, right? They are not closed under addition. And nothing really from linear algebra works when you work with this discrete object. So instead, what we will do, it's slightly related to what Itai asked, is that we'll consider more general functions, still functions from the Boolean cube, but now to the reals. You can also go complex if you want, but reals will be enough for us. Okay, and the cool thing about that is that what kind of algebraic structure does this set has? So what can you do to two functions now that you couldn't do before?
You can add them.
Exactly, we can add them. And we can also multiply them by a scalar, right? Like 5f is also valid. Right? On every input of the Boolean cube, you can look at 5f times 5 or f of what the point is. So that's a vector space. We like vector spaces. Right? So like, resisting the urge of working with Boolean values, and that's actually a recurring theme. You don't want to work ever with Boolean values unless you have to. You want to be more general and then collapse back to this computer science world that we're living in. So once we increase the range to R, you want to do it for other reasons. If you take averages and stuff, you get values in 0, 1, like the interval, right? So, but once you move to R, a field, it's a vector space. And not only it's a vector space, it is a vector space, but it's also a metric space. Even an inner product space. You can put an inner product structure, a very natural inner product structure on this set or on this vector space, right? So I'm going to define an inner product between two functions from the Boolean cube to R. How do you think I'll define it, by the way?
Convolution.
Oh, that will happen as well, but not today. Evolution will be useful, but I'm just going to take, their correlation. To what extent do they agree? So UN is right again. It's the uniform distribution over 0, 1 to the n, as before. Right, that is the amount to which they agree. It's like a kind of like an angle, which what inner product tries to encode or generalize is really correlation, like in direction. Are we directing to the same thing? What's the correlation between us? So I'm going to define this inner product, and it is an inner product. If you remember the definition of an inner product, it's like bilinear, right? It's linear in each of the coordinates, right? The inner product of f and g plus h is the inner product of f and g plus the inner product of f and h. It's symmetric, right? If we had complex number here, you had to worry about conjugation, also putting here and stuff. But over the reads, it's symmetric. And the last thing is that it's always positive, and it's 0 if and only if for the same function, it's always non-negative, and it's 0 if and only if f is 0. But it's kind of clear from here, because when you get f squared, and f squared all being 0 means that f itself is 0. Good. So I don't really. That's kind of a little bit of technicality, but it's an inner product, and one good thing about inner product is that it immediately gives you orthogonality between functions, and once you know functions or vectors are orthogonal, you know that they're also independent, right? They are more than that. They're orthogonal. You definitely can't find a linear combination. They're going in different directions. So, like perpendicular directions. So can you give me, okay, what's the dimension of this space that we are looking at?
2 to the n.
Right. Right, dimension is 2 to the n. You have 2 to the n degrees of freedom here. Right, you can think of all the indicator. You can think of this function as 2 to the n length vector. So it's a 2 to the n dimension. So can you give me like functions that we already saw last time and today? 2 to the n functions that may serve as a good basis for this vector space?
Maybe like the unity functions, like they output everything to 0 except for one element.
Good. So that's the standard basis, and that's a way to see that the dimension is 2 to the n. You can look at the function that indicate a particular input, right? The one on that particular point in the Boolean cube, and otherwise it's 0. But there is a better, like it's okay, but there is something related to small bias sets, like a better basis. Maybe it's not clear it's a basis, and that's why you're not saying it. But can you give me 2 to the n functions that we like?
The characters of the Boolean cube.
Exactly, the characters of the Boolean cube. That's why we're saying Fourier analysis, because it's Fourier. These are the characters. So, right, so let's look at these functions. So let's look at the function. Well, I am going to use this plus minus ones because it's going to be nicer, but let's define phi alpha of x. So for every alpha in 0, 1 to the n, including 0, by the way, which was excluded when we talked about small bias sets, phi alpha of x is going to be minus 1. That's the only tweak I'm going to do about it, to alpha x. Right, so that's a function. Phi alpha is a function. X is an element in the Boolean cube. So when you give me an element in the Boolean cube, well, that function, which is also indexed by an element of the Boolean cube, is this thing. It's either minus 1 or 1, depending on the inner product between alpha and x. But these are, if you think about it, if you remember what we did when we talked about Cayley graphs and talked about characters, these are precisely the characters of the Boolean cube. Because the Boolean cube is a n-fold product of the cyclic group of size 2, whatever, it's a group of size 2, the group of size 2, and the characters of a group of a product of groups is the product of the characters, and the product of 0, 1 is just -1 to x, or the 1 function. So anyhow, these are the characters of the Boolean cube, and we saw them in the context of small bias sets, but actually this is where they should appear first. Like they have a more important role than being like simple functions to full. These are the characters of the Boolean cube. And what I claim is that they are orthogonal. Okay, they're not just, right? So if you take any alpha not equal to beta in 0, 1 to the n, if you take any two of them which are not the same, then the inner product that we have defined between chi alpha and chi beta, by definition, I'm looking at this definition, it's, you should take a x uniformly at random, an n-bit string, and evaluate f and g, chi alpha and chi beta, and take the product, like the real product. Okay. But then, what happens now?
They differ on some thing.
Right. So that's actually good. So I can write it like that. That's another way of good. I understand what you're saying. But you can also write it like that, right? Because it's just the way it works. And the point is that because alpha and beta are distinct, this is a non-zero vector, alpha plus beta. Right? Everything is 0, 1. So this is a non-zero vector. And we said that this thing is 0, right? When you take the expectation, you take a random, completely uniform string, and take the inner product with some non-zero vector, then half of them will be 0, half of them will be 1. So in this -1 power, this translates to 0. Right? Good. So this means that these functions are orthogonal. You have as many as you have the dimension of the space. So this means that this is a basis, right? It's orthogonal basis. Not just basis, it's an orthogonal basis. It's actually also an orthonormal basis, right? Because the inner product of chi with itself, chi alpha with chi alpha, is just 1, right? If you put an alpha here, that's just always 0. And so this thing is 1. Right? So what I'm saying is that the set of 3 alphas is an orthonormal basis of 0, 1 to the n to r of the set of functions from 0, 1 to the n to r. And what do we like to do when we have a basis? Certainly orthonormal, but it's just a basis even. Given a function, what do we like to do?
Span it in that.
Exactly. So given f, because then we understand, its relation to that basis. Sometimes you don't really care about the basis, just a tool, but sometimes it's a useful tool, not just as a way of like concretely presenting things. So given a function, we can express uniquely the function in terms of the basis elements. So, the basis elements are indexed by alphas. And then you have the inner product between the function and the basis element that you are currently iterating over. And then you apply this vector, this basis element. Right? And if you don't like, some people really like x's. So they like putting x. Like they don't like to see f, they see f of x. So but the function is can be written like that. Just by the fact that this is a basis, even before it's orthonormal. And this quantity is denoted as f hat of alpha. Okay? That's the Fourier coefficient of f at alpha. of the alpha Fourier coefficient of f, whatever you decide. Okay, so any function can be expressed like that. Questions? We'll see an example, but just to say, in our context, it's good to have, if you have a PRG for a class, and you want to ask, to what extent is this a PRG for another class, then that's exactly what you should do. You should try to express your function in terms of the functions in the class that you already know how to fool. So we know how to fool these functions using epsilon bias sets. Right? These are the functions we know how to fool. And we just said that any function can be fooled. Any function can be decomposed in terms, or can be written in terms of these kind of basic functions. And so, in a sense, we can fool any function. Maybe it's kind of a trivial way of fooling it. The error is so large that it doesn't give us anything. But I mean, in a sense, using Fourier analysis, we can ask, to what extent an epsilon bias set fool any function. Once we know these values, we'll talk about it more. But that's just the context in which Fourier analysis plays the role it plays in this context. But I think let's look an example. Before even moving on. So let's do AND. I mean, there's no much simpler function than the AND of two inputs. Let's do that. Let's find the Fourier representation, namely this decomposition, when f is just the AND of two n bits, right? Right. So AND is from, just. So, okay, so these are the inputs. So AND is just a function from 0, 1 to 2 to the power of 2 to 0, 1, right? And I guess you know how the function operates. Let's find all of these are called the Fourier coefficients. Let's start maybe with the Fourier coefficient of the alpha, the old zeros alpha, 0, 0. Right, so by definition, maybe I should write the definition here, so I won't forget. So generally, the Fourier coefficient corresponding to alpha of f is kind of by definition the inner product between f and the corresponding character, right? This is the inner product. I just wrote it explicitly. So in our case, we have a very easy job. There are only like 4 elements we are summing over or taking the average over. Right? I should write this thing where here I have the AND function, and alpha is 0, 0 in this case. But here I have the AND function, and this average is over 4 elements. But AND is it gets a value of 1 exactly when x is 1, 1, right? So even though this expectation is only of 4 elements, only one of them survives f, like the AND function, and that's exactly x equals 1, 1. So this means that this is 1/4 3, 0, 0 of 1, 1, which is 1/4. Because 3, 0, 0 is like the inner product between this and that is 0. So -1 to the 0 is 1. Right, in general, by the way, if you have a function and you ask what is f hat of the old zeros vector, it doesn't have to be like 2 bits. What is it? Can you see from here what's going on? When you take alpha to be the 0 vector.
1/2 to the...
It's the average of f.
Exactly, it's the average of f, because you see when alpha is 0, this character is the all ones character. It's always 1. Because this thing is -1 to the alpha x, this character. Here alpha is just a shorthand notation for it. When alpha is 0, this is 1. The inner product of 0 with any vector is always 0. And so -1 to that is 1. So that's always 1, the all ones character that we know. And so all you see is like the average of f. Right? So that's actually nice, right? There is some meaning to. And sometimes people just write like that, even without referring to the distribution. When you write the average of f, you mean the average of f with respect to the uniform distribution. And that happened here as well. The average of n is 1/4, right? Because it's one, exactly one of 4 times. What's the end? What's the Fourier coefficient of 1, 0? So now let's see. So now it's still the case that only one x survives. The 1 1's, right? The 1 1 x is the only one that survives because f is just 0 when you don't feed it 1 1 when f is end. So it will be the same, right? It will be 1/4 chi of 1 0 of 1 1. Right? 1/4 because of the average, and when I'm looking at the one summand, one term in the average that survives, which corresponds to x equals 1 1. And in general, and alpha is 1/4 chi alpha of 1 1, right? When it goes beyond 2 variables. But in that concrete case, what is the chi 1 0 of 1 1? -1. So with the quarter is -1/4, right? Because chi 1 0 of 1 1 is just -1 to the inner product of 1 0 and 1 1. So the inner product is 1, and so you get a -1. What's the inner product? So what's the corresponding character of 0 1? Same. Also by symmetry, right? Has to be the same. I mean, I don't know, we haven't proved it, but it has to be the same. It cannot be something else. And what's about the last one, the all ones character? Not the all ones characters, the all ones input.
1/4.
1/4, right? Because I'm putting here 1 1. So all in all, we can write the end of x1 and x2 as, so I'm collecting the results. So I have a 1/4. So I'm just using this equation now that I know these values. There are 1/4 plus or minus depending on how many bits of inputs do I see. So it's 1/4 minus 1/4. Let me write it very explicitly. This is like minus 1/4. It's this one coming from chi or chi 1 0, but chi 1 0 explicitly is -1 to the x1. And then you have -1 to the x2. When you have a plus 1/4 -1 to x plus x1 plus x2, that's chi of 1 1. And it doesn't look right, but it actually works. It's kind of a weird way of writing things, but it works. Right? Because, for example, if x1 and x2 are 0, then you have a quarter here, but this is 0 and this is 0. So that gives you like a 1 and a 1. So you have like -1/4 coming from here altogether, because it's a quarter minus half. So it's a -1/4, but then this is a plus 1/4, because these are 2 0. So it's 0, right? As it should be. The end of 2 zeros is zeros. And for example, the end of 2 1. So if you put 1 and a 1, you get a quarter plus a quarter, because it's 2 minuses. Quarter plus a quarter plus a quarter plus a quarter, right? Because 1 and a 1 gives you 1 here plus a quarter. So it's a 1. So it looks weird, but that's actually true. Like that holds. It's a weird way of writing things maybe, but that works. You never probably saw ends looking like that. Usually you kind of write it like a product. But yeah, but I meant to write it in terms of the Fourier basis. So good.